first thing we need to do to solve this differential equation is to determine what type of differential equation it is. We can tell that it is a first order differential equation because the highest derivative is dy dx. It's not going to be possible for this to be linear in either y or x because linearity would require that the power of y be 1 or the power of x be 1, and we see we have a y cubed, so it could not be linear in y, and we have x squared, so it could not be linear in x. Another possibility is that this might be a separable differential equation, and that doesn't actually pan out here. If you write this in a slightly different form, you can multiply through by this dx. So you would then get 6x plus 1 times y squared dy plus the quantity 3x squared plus 2y cubed times dx. And 0 times dx is just 0. And if you are checking to see if it's separable, you'll notice that you have a sum of a function of x and a function of y. You need products to be able to make this separable. So it's not going to be a separable differential equation. The other thing you might check for is to see if it's a homogeneous differential equation. And so you would check, actually we put these in the correct order with the dx function first and the dy function, because we're used to seeing them that way. 3x squared plus 2y cubed dx plus, I'm going to actually distribute this function in front of dy. So I'm going to get 6xy squared plus y squared dy equals 0. And to check for homogeneity, I would need to actually plug in mtx ty, and m is this coefficient function in front of dx. And notice when you plug in the tx in place of x, you're going to get the quantity tx squared, which will give you a t squared x squared. When you plug in ty, you're going to get ty quantity cubed, which is going to give you a t cubed y cubed. So you have a t squared and a t cubed, which is going to make it impossible to factor out the same power of t from both of these terms. Remember, homogeneity requires, as a very first step, that you be able to write m of tx ty as t to the n m of xy, which is not going to be possible for this first term. So it's not homogeneous. So if it's not homogeneous and it's not exact and it's not separable, then it is probably going to be an exact differential equation. So let's go ahead and check the partial derivatives, the mixed partials, to see if it's an exact differential equation. So the first thing I'm going to do, this is the m function, this is the n function. The mixed partial means I need to check to see if the partial of m with respect to y is equal to the partial of n with respect to x. So the partial of m with respect to y, so I treat x as fixed, is going to be the derivative of 3x squared with respect to y, which is 0, plus the derivative of 2y cubed, which is going to be 6y squared with respect to y. For the partial of n with respect to x, so I treat y as fixed, I'm going to get, for this first term, y is fixed, so 6y squared is a constant, and then the derivative of x is 1. For the second term, the derivative of y squared with respect to x is just going to be 0. So I get 6y squared for both of these. Since those mixed partials are equal, we have an exact differential equation. So we need to go ahead and calculate the partial integrals of the m function and the n function. So let me rewrite that differential equation. I'm going to take my function. Remember, the solution looks like f of xy equals a constant. So I need to recover f of xy, and that's going to be the partial integral of m, which is this first coefficient function, m dx, and that's the partial integral of 3x squared plus 2y cubed dx. And I'm actually going to get, remember m is the partial of f with respect to x, so that'll come in handy in a minute. But the integral of 3x squared with respect to x is going to be 3x cubed over 3, so the 3's cancel. And for 2y cubed, that's a constant. That comes out, so I'm left with the integral of dx, which is just x. And then I need to put my constant of integration, which because I lose functions of y when I took the partial of f with respect to x in constructing the differential equation, I am going to have a constant that is actually some sort of function of y, h of y. That's my constant of integration. Okay, the next part is I'm going to recover f of xy by taking the partial integral of n with respect to y. And so that is going to be 6x y squared plus y squared with respect to y. And so I treat x as a constant. So 6x is a constant, and the integral of y squared is y cubed over 3. Plus integral of y squared again is y cubed over 3. And because n is the partial of f with respect to y, I would have lost functions of x alone. So my constant of integration is g of x, some function of x. If I simplify, see I get a 2xy cubed plus 1/3 y cubed plus g of x. Now I want to put together the pieces that I got from both of these partial integrals, and I will fill in the missing g of x and h of y functions by looking at both of these. You should check to make sure that your terms that involve both x and y are the same. So notice I have a 2x y cubed here. That is actually the same as the 2x y cubed here. That's the only term that involves both x and y. They match up, so that's good. The g of x then must be this x cubed. That's the only function of x alone. And that means h of y, matching up the functions, must be 1/3 y cubed. So I can use this first function as my solution, substituting this 1/3 y cubed in for my unknown h of y. And then I just need to set this equal to a constant. So the solution is actually f of xy equals a constant. So it's going to be x cubed plus 2x y cubed, just putting it in a different order, plus 1/3 y cubed is equal to c is the solution to that exact differential equation.